Hi chemistry students! This video covers lesson 7 of your general chemistry 1 entitled Chemical Bonding. For the objectives, draw the Lewis structure of ions, apply the octet rule in the formation of molecular compounds, write the formula of molecular compounds formed by the nonmetallic elements of the representative block, and describe the molecular geometry of simple compounds. First, let's define a chemical bond. Chemical bond is the attractive force between atoms or molecules. So this force of attraction that holds atoms together in a molecule or a compound is called a chemical bond. Chemical bonds are grouped into two. One is intramolecular forces. These are the forces between atoms. We have three subtypes of intramolecular forces. We have the ionic bond, covalent bond, and metallic bond. The other group is the intermolecular force or forces. These are the forces between molecules or units to hold them to form the three states of matter: solid, liquid, and gas. So we have four types of intermolecular forces. We have basically dispersion, dipole-dipole, ion-dipole, and hydrogen bond. This video will focus on the two types of intermolecular forces, which are the ionic bond and covalent bond. But first, let us answer the question, why do atoms combine? Why do they tend to combine and form molecules or compounds? Atoms combine to achieve a more stable electron configuration, and stability of configuration is based on the complete distribution of electrons in the outermost shell of the atom. Octet rule states that an atom loses, gains, or shares electrons to obtain 8 valence electrons and become stable. For the atom to become stable is to attain the same configuration as the nearest noble gas from it. In understanding the formation of chemical bond, we will use the Lewis dot structure by Gilbert Lewis. This consists of the symbol of an element and one dot for each valence electron in an atom. So we have here a general structure or representation for the Lewis dot structure of an atom. We have the X that represents the symbol or a symbol for an element surrounded by 8 valence electrons. That's why it's called octet rule, because of the concept 8 valence electrons. Although an atom may have less than 8 electrons to become stable, and we will have that to talk about that later on. Let's have, for example, hydrogen. Hydrogen's atomic number is 1. So you will see here the electron configuration of hydrogen, which is 1s1. So for the Lewis dot structure of hydrogen, we have the symbol of hydrogen H, and then surround it with 1 dot to represent its 1 valence electron. Helium has 2 atomic number. Its configuration is 1s2. So for its Lewis dot structure, you indicate the chemical symbol of the element, which is He, helium, and then surround it with, you put 2 dots to represent the 2 valence electrons. In the case of elements with atomic numbers 3 and higher, you have configuration with several orbitals. So in the case of lithium, we have atomic number 3. So to distribute 3, we have 1s2, 2s1. Anyway, by the way, we have here their orbital filling, which we have discussed last time in the previous video rather. So in the distribution of electrons in the atom of lithium, you have 2 energy levels available. So for the valence electrons, you will consider the outermost shell or energy level, the last occupied energy level. So in the case of lithium, it's 2. And in that energy level, we have 1 orbital, which is s. And in that orbital, we have 1 electron. So that gives us the number of valence electron for lithium atom, which is 1. So for the electron or Lewis dot structure, you write the symbol Li for lithium and you put one dot to represent one valence electron. Beryllium has atomic number 4, so its orbital filling is as follows. We have configuration 1s2, 2s2. So like lithium, the outermost shell or energy level is 2. But unlike lithium, the number of electrons distributed in the s orbital in the second energy level, 2. So to indicate 2 valence electrons for the beryllium atom, we have the symbol of beryllium Be, and you put or surround the symbol with 2 dots to represent the 2 valence electrons. To easily determine, using your periodic table, the number of dots or valence electrons and determine or draw correctly the Lewis dot structure, you may use the group number. For example, in 1A family, wherein we have hydrogen, lithium, sodium, potassium, and few others, they have the same valence electrons. So the group number gives all the elements in the same group the number of valence electrons. So in the case of the elements in 1A, they have the same number of valence electrons, which is 1. So for hydrogen, lithium, sodium, potassium, and the rest in 1A, they have the same valence electron 1. Therefore, they have the same Lewis structure with 1 dot because they have 1 valence electron. So we have hydrogen 1s1, lithium outermost 2s1, sodium 3s1, potassium 4s1. So all of them have the same number of valence electron, which is 1. Same with 2A and the rest of the representative family elements, which are 1A, 2A, 3A, 4A, down to 7A. So in the case of beryllium, magnesium, calcium, which are all in 2A, they have the same number of valence electrons, which is 2. So you will notice the same number of valence electrons but different outermost shell. So beryllium's outermost energy level or shell is 2. Magnesium is 3. Calcium is 4. All of them have the same number of valence, so they have the same number of dots surrounding their chemical symbols. For the noble gases, except the first from the top, helium, all of them have the same number of valence electrons, which is 8. So with the exception for helium, we have 1s2. So it's already given that it has 2 valence electrons. So its electron configuration 1s2 gives it the number of valence electrons 2. So you surround it for the Lewis dot structure with 2 dots. From neon, argon, krypton, radon, and the rest of the noble gas family, they have the same number of valence electrons, which is 8. So neon is across second energy level, or across period 2, so its outermost energy level is 2. Argon is across period 3, so outermost shell or outermost energy level is 3. But they have the same number of valence. So just add up the number of electrons in the orbitals in the same energy level, in the same outermost energy level. So in the case of neon, we have S and P in the same energy level 2. So you just add up 2 and 6 to have 8 valence electrons. And then you surround the symbol with 8 dots to represent the 8 valence electrons. So you will see here a summary of the Lewis dot structures for the representative elements from 1A, 2A, 3A, and so on. So you will see again that the group number gives the number of valence electron, which is similar for all the elements in the same group number. Let's have the following elements. Can you identify which are metals and non-metals? So these 4 elements, aluminum, calcium, lithium, and beryllium, are all metals. And all the rest in the list are non-metals. In the periodic table, we have majority metals. We only have a few non-metals, and we have much fewer metalloids. The metals and non-metals are separated by this ladder-like structure here, which are the metalloids. Going back to the question, why do atoms combine and form chemical bonds? So we have answered this question earlier. To attain stability. And for an atom to become stable is to obtain the same configuration as the nearest noble gas from it. But for the discussion of chemical bonding, we have to take note of the general tendency of metals and non-metals. So during chemical bonding, metals tend to lose or give up electrons, while non-metals tend to gain or accept electrons. Metalloids, on the other hand, have properties that are intermediate between metals and non-metals. So they're metalloids that may gain or give up electrons. Let's have oxygen. Oxygen, as we all know, is a non-metal. So recalling the tendency, we have to accept or gain electron for non-metals. So for this atom to gain stability, it has to accept or gain electrons. So how is it possible? Or how is it explained in a molecular level? So we have the electron configuration of oxygen 1s2, 2s2, and 2p4. So the outermost energy level again is 2 with 2 orbitals in that same energy level s and p. We have 2 electrons in the s orbital and 4 electrons in the p orbitals for a total of 6 valence electrons. The 6 valence electrons are represented here in the symbol with dots. So we have 6 valence electrons. Oxygen is surrounded with 6 dots for that 6 valence electrons. Since oxygen again is a nonmetal, it has to gain electron to become stable. To become stable as the nearest noble gas from it, which is neon. Neon is one of the noble gases, and the noble gases are the most stable representative elements in the periodic table. The configuration of neon is 1s2, 2s2, and 2p6. Notice the difference in the number of electrons in the p orbitals of oxygen and neon. Neon has 6 in its outermost p orbital, while oxygen has only 4. So for oxygen to become stable as neon, it has to gain or accept 2 electrons. Gaining 2 electrons will have to add 2 electrons to its original number of electrons, 8. From its ground state configuration, we have 8 plus 2 equals 10. So 10 to distribute 10 electrons is to have the same configuration as neon, which is 1s2, 2s2, and 2p6. So this is for the non-metals. What about for metals like sodium? Sodium is metal with the configuration 1s2, 2s2, 2p6, 3s1. The nearest noble gas from sodium is also neon. But first, let's take note of the number of valence electron. The outermost energy level for sodium is 3, with only 1 orbital available, which is s, and with only 1 electron distributed in that s orbital. So that gives us 1 valence electron, and to represent that in its Lewis dot structure is 1 dot here. So again, the nearest noble gas is neon. The configuration of neon is only up to 2p6. So as you can see here, sodium has excess configuration 3s1. In order to become stable as neon, being a metal, it has to lose electron. The question is, how many does it have to lose? The excess of 1 electron. After losing one electron from the original number 11 from its ground state configuration 1s2, 2s2, 2p6, 3s1, minus 1 will have 10. So having 10 electrons is having the same configuration as the nearest noble gas, which is a stable atom from sodium, which is neon. So that is for metals. Let's now go to the first type of intramolecular force between atoms, which is ionic bond. Ionic bond forms when a metal transfers electrons to a non-metal. So notice there is transfer of electrons. So ionic bonding involves transfer of electrons, and the transfer is always from metal to non-metal, because as we have emphasized in the previous slide, metals tend to give up or lose electrons, while non-metal tends to gain or accept electron. Let's have an example. We have lithium as the metal and fluorine as the non-metal. So notice the electron configuration of lithium 1s2, 2s1. Being a metal, it has to give up how many electrons? 1 electron. The available valence electrons, it has to be given up by the atom of lithium. On the other hand, fluorine has 1s2, 2s2, 2p5. So this is deficient of 1 electron to have configuration of 1s2, 2s2, 2p6 and become stable. So what happens is lithium will transfer its available valence electron to fluorine. As that happens, lithium will become positively charged and fluorine becomes negatively charged. So ions are formed when the two combine to form the ionic compound lithium fluoride and giving each atom stability. So the transfer of electron is from lithium to fluorine. One electron is transferred from the atom of lithium to the atom of fluorine, resulting to formation of positive lithium and negative fluorine ions to form the ionic compound lithium fluoride. Another example is the combination of calcium, another metal, and oxygen, another non-metal. Open and close brackets argon 4s2 is the noble gas configuration of calcium. We have studied this in the previous lesson. Oxygen is 1s2, 2s2, 2p4 ground state configuration. So we have two available valence electrons from calcium to be given up for its stability, while oxygen needs to gain 2 electrons to become stable, to have 8 valence electrons. So what will happen here is calcium will transfer its 2 available electrons to oxygen, giving oxygen stability with 8 valence electrons and a charge of -2. So -2 here indicates gain of 2 electrons, while +2 charge for calcium indicates loss of 2 electrons. This results the formation of the ionic compound calcium oxide. So notice their stable configuration becomes that of the nearest noble gas from them, argon and neon. Another example is the combination of magnesium metal and nitrogen non-metal. So we have 2 valence electrons available from one magnesium atom, while one nitrogen needs to gain 1, 2, 3 because it only has 5. So to complete its octet, 8 valence electrons, it has to gain 3. If only 2 are available from one magnesium, then it has to give up its 2 available valence. Only it will be deficient by 1 more. So it has to get another from another magnesium. So that another magnesium will give 1 electron to 1 nitrogen. It will have an excess of 1. Where will it go? Then we have to add another nitrogen. So that excess from another magnesium will go to another nitrogen. But this another nitrogen will lack 2 more. That's why we need another magnesium to get 2 more electrons. So this additional magnesium will have to transfer its 2 available electrons to magnesium. So as a result, as summary in the in the ionic equation, we have 3 atoms of magnesium lost 2 electrons each to 2 nitrogen atoms, which needed 6 electrons all in all. So as a result, again, we have each of the 3 magnesium lost 2 electrons, obtaining a positive 2 charge. 2 nitrogen gaining 3 electrons each from magnesium atoms, also each gaining negative 3 charge, forming the ionic compound magnesium nitride. Let's now have covalent bonding. Covalent bond forms when nonmetals share electrons. So unlike ionic bonding, which involves transfer of electrons, covalent bonding involves sharing of electrons. So let's have these 2 nonmetals which are similar, hydrogen and another hydrogen. Notice the position of valence, the dot. So you can interchange the position of valence electron or dot for as long as you can illustrate clearly the sharing of bond in covalent bonding. So in the case of formation of hydrogen molecule, here we have 1 hydrogen with 1 dot to represent its 1 valence electron, combining with another hydrogen with the same number of dot, 1 or valence. Since both of them need to gain electron because both of them are nonmetals, again, from the general tendency of the nonmetals to gain electron, they need to gain electrons to become stable. And hydrogen does not need to gain 8 electrons. It just has to gain 2 to become stable. So by sharing 1 electron, the 2 atoms gain their stability. The nearest noble gas from them is helium, and helium has only 2 electrons. This shared pair of electrons can be represented by a dash or a line between the 2 atoms. So that one line means there is 1 shared pair of electrons. So that bond is a covalent. Let's have another example. Fluorine is one of the halogens together with chlorine, bromine, and iodine. So one fluorine, like chlorine, bromine, and iodine, have 7 valence electrons. Belonging to 7A means they have the same number of valence electrons, which is 7. So one atom of fluorine needs to gain 1 to obtain 8 valence electrons and complete its octet and become stable. So when combined with another fluorine, it has to share electron with that fluorine. So when these two share electrons, both will have the same configuration as that of the nearest noble gas from them, which is neon. Now counting the octet, we have 2, 4, 6, 8 for fluorine. Take into consideration in counting that shared pair of electrons. So each of the fluorine atoms has gained 8 valence electrons and therefore has obtained its stability. Or you can represent that shared pair of electrons by a dash between the symbols. Covalent bonding with equal sharing of electrons occurs in diatomic molecules formed from one element. In addition to fluorine, we have hydrogen, chlorine, iodine, and nitrogen. Unlike the first three, nitrogen shares 3 pairs of electrons. 2 nitrogen atoms share 3 pairs of electrons and therefore forming a triple bond. We call these substances where covalent bond exists as molecules. For example, carbon dioxide. It exists individually bonded covalent molecules containing 1 carbon. So one molecule contains 1 carbon, as you can see here in the representation of the molecule, and then 2 atoms on the side, bonded with that carbon. Another molecule is the hydrogen chloride. This is a polar covalent bonding. Notice hydrogen is partially positive and chlorine rather, is partially negative. Chlorine has a greater attraction for the shared pair of electrons. That's why the shared pair of electrons is closer to chlorine, because it is more capable of attracting electrons than hydrogen. The attractive force that an atom of an element has for shared electrons in a molecule or a polyatomic ion is known as electronegativity. So in this case, chlorine is more electronegative than hydrogen. Electronegativity values can be seen in the periodic table. So we have here a summary of the electronegativity values. We have trends in electronegativity. From top to bottom, within a group, it's decreasing. From left to right, it's increasing. So we have, for example, from top to bottom, fluorine is 4, chlorine is 3. So it gets lower as you go down within a group. On the other hand, across a period, as you move from left to right, electronegativity tends to increase. You can determine the band polarity according to electronegativity differences. So if it's less than 0.4 difference, then it is more non-polar covalent bond. If it's between 0.4 to 1.8, it's more polar covalent bond. If it's greater than 1.8, it is more likely ionic bond. If the electronegativities are the same, the bond is nonpolar. Automatically, for example, in this molecule, we have 2 similar atoms. So they have the same electronegativity values. So the electronegativity difference will be 0. There. Another is hydrogen. Hydrogen's electronegativity is 2.1. So getting the difference, you will also get 0. What about 4 dissimilar atoms? In this case, chlorine is more electronegative. Therefore, most likely the electronegativity difference is greater than 0.4. Which in fact in this case is 0.9. So that falls between the range 0.4 to 1.8, and therefore this molecule is polar covalent bond. There is an equal sharing of electrons. One is more electronegative than the other. So that's how we identify a molecule as polar or non-polar. And then if electronegativity difference is higher than 1.8, like in that case, then ionic. The following are polar. So the arrowhead is towards chlorine, meaning chlorine is more electronegative than hydrogen. There is an equal sharing of electrons. Same with hydrogen bromide. Water, oxygen is more electronegative than hydrogen, so there is an equal sharing of electrons. The dipole moment is towards oxygen, and therefore the molecule is also polar. A molecule containing different kinds of atoms may or may not be polar depending on its shape. So aside from electronegativity difference, you can also determine the polarity of molecule according to shape. For example, in carbon dioxide, the carbon dioxide molecule is nonpolar. Why nonpolar? Because its carbon-oxygen dipoles cancel each other by acting in opposite directions. So dipole moments are cancelled out. There is symmetry in the shape, and therefore the molecule is considered non-polar, fall under non-polar. There are guidelines in naming molecular compounds. Molecular compounds with one atoms like HF and SiC, you use suffix IDE for the second element. So you name the first element completely. So in this case, we have hydrogen fluoride, and number 2, we have silicon carbide. Guideline number 2, prefixes are used to denote the number of atoms of each element in the formula. For the first element with no subscript, meaning 1, you don't need to use mono. The second element, whether it has a visible subscript or none, for 1, you always use a prefix. So the following are the prefixes used in naming binary molecular compounds. So for this set of example, we have carbon monoxide and carbon dioxide. Diatomic molecules like the following are given the name molecule or molecular. So for example, H sub 2, so that is called hydrogen molecule or molecular hydrogen. Can you write the chemical formula of the following? Chlorine trifluoride is ClF sub 3. So we have 1 chlorine and 3 fluoride. So you just take a look at the prefix that is used in the name. So trisilicon, tri means 3 silicon, Si3, and tetra means 4. So N sub 4. Di means 2, so we have N sub 2. Tetra again means 4, so tetrahydride is H sub 4. Triiodine is 3 iodine 3I, I3. And monoxide from the prefix nona, meaning 9. So we have O sub 9. Hepta means 7. So N 7 heptanitrogen, trisulfide 3 sul 4. So that's how we name binary molecular compounds. Let's go to molecular geometry. Molecular geometry is the three-dimensional structure or arrangement of atoms in a molecule. This considers Lewis dot structure, valence shell electron pair repulsion, VSEPR, and bond angle. It helps us determine a compound's polarity, reactivity, phase, or other properties. Let's take note of the different octets. We have incomplete octet. The first 5 elements are exempted from the octet rule. They do not have to obtain 8 valence electrons to become stable. What are these elements? We have hydrogen, helium, lithium, beryllium, and boron. So you will see them in molecules with less than 8 valence electron. We also have expanded, meaning the atom has more than 8 valence electrons. Most of these elements are located in the 3rd period of the periodic table and beyond, like phosphorus, chlorine, bromine, and others. And then we have complete octet, mostly in the 2nd period. Let's have some examples. So we have here molecular hydrogen, molecular fluorine, and molecular carbon dioxide. All of them have the same shape, linear. Angle is 180, and all of them are non-polar. Same element will have electronegative difference of 0, while for carbon dioxide, we have canceling out the dipole moment, equal distribution of electrons. Another example is boron trifluoride. So notice the shape of the molecule. We have trigonal planar. So each angle is 120. It is also non-polar because of symmetry or equal distribution or cancelling out of dipole moment. And we have sulfur hexafluoride. The shape is called octahedral. We have 2 angles. The molecule is also non-polar. We have here the summary of the shapes of molecules. We have linear with 180 degrees. Example is carbon dioxide. We have here examples of the molecular structure. We have trigonal planar with 120 degrees angle. Example is BF3 or boron trifluoride. That's we have seen in the example earlier. We have bent, like sulfur dioxide, bent because of the VSEPR effect. Atoms are being pushed because of the strength of lone pair or non-bonding electrons. Tetrahedral, we have same angle, 109.5 degrees. One good example is the methane, CH4. We have trigonal planar with 107 degrees. Example is ammonia. We have angular, trigonal bipyramidal, seesaw, T-shaped, linear, octahedral, square pyramidal, square planar, and pentagonal bipyramid. Can you give the shape of the following molecules? So what do you notice? All of them are linear. You can try to draw the Lewis structure to determine the shape of the following molecules. So with that, you can have more time studying other sources in order to gain better understanding of the topic on chemical bonding. Thank you for watching.